Hello, boys and girls. Today we're going to talk about polarity. The first thing I want to bring up before we look at the polarity between two atoms is I want to talk about the three kinds of bonds we've discussed lately. What are the three kinds of bonds? We've discussed ionic, polar covalent, and nonpolar covalent. And you should well know that in the covalent ones we're sharing electrons, and in the ionic we're transferring electrons. Well, how does that really happen, you should ask yourself. And you know that we talked about an ionic bond being between a metal and a nonmetal, and polar covalent bonds are, all covalent bonds are between two nonmetals. I'm not writing the word metal, you know that non means nonmetal. So yeah, but why does that work? Well, in order to talk about why that works, we need to remember electronegativity. So up here at the top I'm going to write electronegativity. The word takes me forever to write, electronegativity. And what is this? This is attraction for electrons. That's the shortened down version. Attraction for electrons, how strongly an element pulls electrons towards it. And you should remember that the most electronegative is fluorine. So closer to fluorine we are, the more electronegative. So how can we use electronegativity to predict what kind of bond it is? Well, we can look at the difference in electronegativity. So the difference in electronegativity. Say, for example, we're looking at cesium and sulfur. Cesium and sulfur. Now, we know that's going to be ionic because cesium is a metal, but why is it ionic? Why does cesium want to give electrons to sulfur? Well, let's look at that. We can look at the En difference. En difference. We can say, okay, cesium's electronegativity is 2.5. I'm looking these up in the book. You don't have to memorize these. And sulfur's electronegativity difference is 0.7. And when we subtract those, we get 1.8. And what we've said as scientists, and this is just an arbitrary number, but what we said is that an ionic bond is an En difference of greater than 1.8. Greater than 1.8. So, excuse me, why did I say 1.8? My bad. 1.7. So what's the deal with everything else? What if it's exactly 1.7? Well, then you're kind of getting into a gray area, so to speak. So, but big electronegativity differences are ionic. Why is that? Because this element has a very strong attraction for electrons. It's tugging electrons. And these metals have very weak attractions for electrons, for its outer electrons, its valence electrons. So what happens? It just goes, and the sulfur just pulls that electron essentially completely away from the cesium because of that big electronegativity and that small electronegativity. What about a polar covalent bond? I'm going to choose hydrogen and sulfur as my example here. Hydrogen and sulfur. Whoops, I forgot to change out of that pink color. Pink, that's not very manly. Hydrogen and sulfur, manly. There we go. Look, isn't that better? Yep. Okay. So hydrogen and sulfur, the difference in electronegativity. Hydrogen has an electronegativity of 2.1. Sulfur has an electronegativity of 2.5. So the difference is 0.4. Now that's not big enough to be ionic. So in this situation, the difference in electronegativity is not big enough for that sulfur to completely rip off that an electron for hydrogen. So what do? Well, they end up sharing the electrons unequally because there's not enough of a difference to have the electron completely transfer. That's a great thing to write down right here. In the polar covalent, somebody's winning, but it's not a big enough difference to transfer the electron. And so how do we identify polar covalent? We normally say 0.3 through 1.7 is going to be polar covalent. What does that look like? Well, let's look at it. Let's let this dot be, no, let's just use an H. If H is hydrogen and S is sulfur, sulfur's more electronegative, so it's going to pull electrons towards it. So this is what happens to the electron cloud. The electron cloud gets shifted and sulfur gets a fatter electron cloud. It's pulling electron density or electron charge towards it. Now this automatically does something to this molecule. This gives the molecule a positive and a negative end. So it lets this end be a partial positive and this end be a partial negative. This is the sigma Greek letter. That's the Greek letter sigma. I'll just make an S and go all the way around and then put a plus or a minus on it. So wherever the electrons are pulled will be partial negative. That's partial negative. In other words, we didn't transfer the electron completely, but it spends more time over there, so that has a negative end. That's what makes it polar. The term polar means having poles. So this molecule, this H and this S bond, the S has a negative end and the H has a positive end, and that's how it has poles. We'll talk more about those poles later. Now, in a nonpolar covalent, we have still two nonmetals, but they're going to be really close to each other in terms of electronegativity. Like, for example, making it up off the top of my head, how about fluorine bonded with fluorine? Well, fluorine is 4.0. Fluorine is 4.0. The En difference, En diff means En difference in electronegativity is 0. So in this case, nobody's stronger than the other one. They share equally. They're a tie. What do their electron clouds look like? Oh, before we do that, that means that we let nonpolar be like from 0 to 0.3. Now, depending on if you went to a different website, you might find different values for electronegativity difference, because in reality, it's like a sliding scale. Some things can be more ionic and less covalent. Some things can be more covalent and less ionic. But in general, we like to divide them up into these three categories. Okay, so what is the electron cloud going to look like here? Pause it and draw it yourself and then look to see if you're right. Since they both tug equally, they have this same ugly, the same size electron cloud. That doesn't look the same. That doesn't look like the same. Let's do it again. They have the same size electron cloud. Because this guy tugs the same as this guy, nobody wins the battle. And if no one wins the battle, that makes it non-polar. Now there's no partial positive. There's no partial positive or partial negative on this one because they're tied. They're equal. They're pulling with the same power. Okay? So when we're looking at a pair of elements, this says polarity between two atoms. When we're looking at a pair of elements, this is how we can determine if that pair of elements would like to form an ionic bond, a polar covalent, or nonpolar covalent. We can look at the electronegativity difference. In general, ionic bonds are metal and nonmetal. Polar covalent bonds are two nonmetals that aren't next to each other, and these guys tend to be nonmetals that are side by side, and even some of those aren't. I normally won't give you any that are kind of in between. Okay? So that's polarity of bonds when we're looking at just a pair of atoms. What does it look like? What do we do when we have molecules? Let's circle this and move this up here. Come on up here, molecules. What do we do when we look at a molecule? Now, a molecule can consist of only two atoms. In that case, we do what we just did up top. But what if the molecule has 3 or 4 atoms, or 5 atoms, or 6 atoms, or 1,000,000 atoms? Oh my gosh, 1,000,000 atoms? Is there a molecule that has 1,000,000 atoms? I bet there is. Like, check this guy out. Let's just look at this guy. Let's look at CO2. This is interesting. Here's CO2's shape. It's linear. So when we look at CO2, we have to think about symmetry and think about a tug-of-war. Look at the central atom. I can kind of divide it down the middle. This oxygen is fairly electronegative. It pulls that way. This oxygen, though, is fairly electronegative and pulls this way. Who wins the tug-of-war? The answer is no one wins the tug-of-war. This is a nonpolar molecule. Carbon dioxide is a nonpolar molecule because the atoms' electronegativities cancel out, or let me say it a different way, their pull for electrons cancel out. No one wins the tug-of-war. No one wins the tug-of-war. That's really the key. If you can think of it as tugging, then you can figure out whether it would be polar or nonpolar. What if I go over here, though, and I change that F? Let me not do that. Let's not do that. That might confuse someone. What if we go over here and we do this molecule? carbon monoxide. This is carbon monoxide. Oxygen has a certain pull, an electronegativity. Carbon has a certain pull. Do they tie or does someone win? That's oxygen winning. That was going to be a star and I changed my mind. Oxygen wins. Oxygen's very electronegative. So we get an overall pull of electron density, or electrons get pulled more towards oxygen. So this is a polar molecule because oxygen wins. Oxygen wins. That gives a partial negative over here where oxygen pulls and a partial positive over here. Those are the sigma signs that you saw earlier. Note, please, that oxygen is more electronegative. That's how I knew that it pulled electrons over that way. Yeah, okay. What about, now these are easy molecules. Let's get to a more challenging one. Let's do sulfur dioxide. Sulfur dioxide ends up looking like this. This is sulfur dioxide. Now, when you look at that, boys, girls, men, and women, when you look at that, do you think tug of war? It's like a three-way tug of war. We've got oxygen here pulling, we've got oxygen here pulling, and over here we've got a lone pair pulling. What happens on this molecule? Well, you should easily see that this is a polar molecule that... Okay, so I paused the video, so I don't remember where I was, but I want to say this about sulfur dioxide. The presence of this lone pair means that there's no way for the tug of war to be a tie. Someone has to win, and so the presence of a lone pair on the central atom automatically indicates that this is a polar molecule. Everybody labeled this one polar. Let me go to a more challenging one, though. What about like carbon tetrachloride? That's one that I had you do in the Vesper and Lewis structure worksheets. Carbon tetrachloride ends up looking like this, or methane. They're all tetrahedral, all the tetrahedral ones. What about this one? Who wins this one? Now, if you looked at just carbon and chlorine together on their own, that is polar. Chlorine definitely tugs electrons. I'm going to make that a different color. Chlorine definitely tugs electrons more than carbon because it's more electronegative. So chlorine pulls over here. But what happens when all four chlorines pull equally? Remember now that in a tetrahedral molecule, they're all evenly spaced. What happens when they all pull equally? Like a tug of war, like a three-dimensional, four-person tug of war. What happens if they all tie? The answer is all of these polar bonds, all of these individual polar bonds, get ready, cancel each other out. And we get a non-polar molecule. That's very important, a non-polar molecule. So you need to look at each one and figure out whether the bonds will all cancel out and will be nonpolar or whether they won't cancel out. Now, what happens if I took that same molecule and I put C and I put F here, Cl here, and Cl here? Will that cancel out? Well, no, because the CF bond F is more electronegative, so it's going to shift electrons towards F. So electrons are going to get shifted that way. So this is a polar molecule. All right. So if you're looking for a short, easy way, I can give you a short, easy way to recognize molecules' polarity. Number one, if it has lone pair on the central atom, it is polar. No questions asked. Or number two, if the central atom, Ca is going to be central atom, is surrounded by different elements, it is going to be polar. Remember, lone pair on the central atom, polar. Central atom surrounded by different elements, polar. These are the things that are polar. So if you're not those, then you are nonpolar. And why do we even care about this? Remember that shape predicts behavior. The end.